Hey, AP Calc crew, Mr. A here. We're going to focus on lesson four, optimization. This is so that you can use it in preparation for your quiz and so that we have a little extra time to practice in class. So, optimization is when we take our original function and our first and second derivatives and kind of apply them to a real world example. Um, and we use general steps for solving optimization problems. One is we're going to take the derivative. We'll find critical points, use a sign to determine increasing and decreasing, or our second derivative to determine concavity, and then substitute in critical points to separate local and global extremes. So the first thing we want to do, here's an example, use calculus to find two numbers whose sum is 24 and whose product is as large as possible. Now, a lot of students will just kind of guess and check and be like, you know what? The first thing I normally hear them say is 11 times 13. Oh, wait. How about 12 times 12 if the numbers can be the same? Yeah, sure. This case would be 143 and this would be 144. And they realize that as long as the numbers are the same, that works out. Well, we need to use calculus to actually find these. So the first thing we're going to do is list out um, a particular scenario where two numbers added together would equal, so the sum is 24. Now, really, we should say find two non-negative numbers. Let's just stay in the positive range here, so that when they multiply together, they are as large as possible. Well, this is our restriction function. It's our restriction because we can only go as high as 24, no matter what. The thing we're trying to optimize, our optimization function, is going to be a combination of x's and y's where we multiply them together. Now, I've seen it written this way. I've seen something like this, p max of x, where we're looking for the product, the maximum product. I like to write it as xy. So we have, this is going to be our optimization. This is what can change based on what numbers we substituted to it. No matter what, x plus y always has to equal 12. But x times y is going to be is the thing we're looking to optimize or to maximize. So now we can find the derivative. Whoops. We can find the derivative. We know how to do that. Except instead of using implicit differentiation, I would rather just put this in terms of x's. So why don't I take my restriction function and call it 24 minus x and substitute in. So my new equation, just in terms of x, which is going to be much nicer, is just going to be x times 24 minus x. We'll clean this up, call it 24x minus x squared. Now, this equation, our optimization, will occur when will maximize or minimize at a derivative where it doesn't exist or where the derivative is 0. So 24 minus 2x is my derivative. We are looking to see when the derivative is equal to 0. So 0 is equal to 24 minus 2x. 2x equals 24. X equals 12. We have found an x equals 12. Go back to the original restriction. 12 plus y equals 24. So y equals 12. We get x, we get f of 12 comma 12 is going to be 12 times 12, pulling that out of here, which is 144, which should be my max. Now, how do I know it's a max? Well, I should have done these steps prior. So I'm going to take my derivative. So this step should really come before the others. And we are going to test that derivative. Oh, here, I'll just jump right over to the first derivative test. So I'm going to take my number line. The number 12 is a possible critical point. We test a number anywhere before it. Let's do the number 10 because that's pretty easy. And let's do the number 15. We put 10 in, we evaluate 10 into the derivative, and we're going to get 24 minus 20, which will be positive, and then 15 would be 24 minus 30, which is negative. So we have a function that is increasing and decreasing like this, so we know that 12 is going to be a max. Now, something else we could have done, we could have actually found the second derivative. Well, what does the second derivative tell us? 24 minus 2x, derive that, we get negative 2. This means it is always concave down. So if a function is always concave down, then we would have a maximum there. So that's another way of testing it. Yeah, so we have everything that we need to determine the maximum amount. Now, we are supposed to test endpoints. So if we did that test, we would do f of 0 and 24. If x was 0, y would have to be 24, which would be 0 times 24, which is 0. And 24, if x was 24, and y would have to be 0. So I get 24 times 0 equals 0. Now, kind of redundant, but you do have to test endpoints each and every time just to make sure that you have your maximum minimum. Now, we understand that that should be lower because we've already done the first derivative test. We've also found the second derivative, which should signify that we have a max there, but always test your endpoints so that you know that you're in a good spot. Here's a little bit more complicated example. So here's steps to applied optimization problems. We're talking, a rectangular box. We're talking if I have a can and I want to minimize the amount of surface area because we would save aluminum that way. We're talking about if I have maybe a function trying to find the closest spot from one spot to another. There's plenty of examples. There's always this famous one where you have buildings and you have a wire going between the two buildings, trying to minimize that wire that goes between the two buildings. Where do you put it? Here, so that you minimize that wire. So we're going to get into some of these today. All right. So we need to draw and write down what we know and what we need to know. Set up constraints. It's also called a constraint. I call it restrictions, but constraints. Same kind of vocabulary here. An optimization equation. Solve the constraint to substitute in to the optimization equation. Use optimization to find critical points and answer a question and check yourself. Like if we get an answer that doesn't make sense, like negative volume, we're in the wrong spot. So you plan to make an open rectangular box 8 inches by 15 inches from a piece of paper. Call it a piece of paper, aluminum or tin, anything, but it's going to be an open rectangular box. We are cutting congruent squares, so that's pretty nice. The shape that the geometric figure that we're cutting out of it is consistent, and we'll be folding those sides up. What are the dimensions that will maximize the volume? What is that volume? Okay, so first thing we're going to do is draw I'm going to draw a rectangle. Now, there's different ways to draw this. You could say that we're going to cut out squares from the edge here. If I were to cut out this square, it's going to be a square on both sides. This is my new result. Really, it's a smaller rectangle. Not smaller rectangle, but right here, it's going to have flaps. It's going to have a flap here, a flap here. Oops, that's way too large. Sorry about that. Here and here, because when you cut it out, it's going to have a height of x. When you go to fold that up, you now have that height of x right there. The x's will meet. Those x's will meet and will be x high. The problem is that when you cut it out, this 15 here, what is it, 15? Oops. So let me label this one as 15, because the initial one was 15 by 8. The new one is actually losing from both sides. It's losing a distance here. So when you go to fold that up, you're going to lose out. Let's say it was an inch. You would lose an inch on this side, and you would lose an inch on this side. Same thing going in this direction. You would lose an inch and an inch. So if I'm going to call that x, I'll actually label this as 8 inches, 8 minus 2x. I'm sorry, wrong dimension. 15 minus 2x, 8 minus 2x. Again, the reason for that, you're just taking it out of both sides. So when it folds up, it's still only going to be x high because where they meet, they're going to meet like this. It's only going to be x high when you get there in height, but because they're both meeting at that location, we are taking away the 8 minus 2x from both sides. So let me start with my restriction. Always start with the restriction or the constraint. I'll label it constraint this time. R-A-I-N-T. Okay, I spelled that right. Constraint. What I know is that no matter what, the height will have to be greater than 0. Right? And I also know that this side has to be greater than 0 and this side has to be greater than 0. So I'll take 8 minus 2x and make it greater than 0, and I'll take 15 minus 2x greater than 0. So all three versions have to be greater than 0. We can't have a negative here. So this one's already solved for us. We have, we have negative 2x is greater than negative 8, and negative 2x has to be greater than negative 15. Divide both sides by negative 2. Whenever we divide by a negative, the sign changes direction. So we have to change that to 7.5. Okay. Now, we have three things. We know that no matter what, the height has to be greater than 0, or the amount you're cutting out has to be greater than 0. We have to have a constraint. It has to be less than 4 and less than 7.5. Well, listen, let's say we have an answer of 6 when I'm all said and done. If that answer is 6 and I go to put it in here, it's going to work fine. Put it in here, it's going to work fine. Put it in here, it's not going to work fine. 8 minus 12, negative 4, you'll have a negative volume. So we have to ignore this restriction and focus solely on the most restrictive. The most restrictive is greater than 0 and less than 4, and greater than 4. Sorry, less than 4 for what I'm cutting out. So I'm going to say that my domain of x's has to be 0 less than x less than 4 inches. I'll throw inches here as well. 0 inches to 4 inches has to be my domain. Okay. Let's take our volume. So what we are maximizing is our volume. So volume is length times width times height. We want to know when that's 0. Now back here, this is my restriction and constraint. I just did the same thing here. So we're done with that step. We're ready for volume. Volume of a box is length width height. That's going to be x times 8 minus 2x times 15 minus 2x. Do this workout, clean it up. I'm going to leave the x out front. We get 8 times, that's 80, it's 120. Take away 16x, take away 30x, plus 4x squared. I'm going to distribute the x across. Feel free to pause if you need to follow my math. And I'm also going to rearrange and clean everything up. So 4x cubed, that's 30, 46. So minus 46x squared plus 120x. We are interested when the volume of my box is equal to 0. The derivative is equal to 0. So the volume is equal to 0. So volume is going to be equal to, the derivative is 12x squared minus 46 times 2 is 92 plus 120. The derivative, 0 equals 12x squared minus 92x plus 120, I believe, is what we get. for the answer for our derivative. Now, sometimes it is factorable, other times we go straight to the quadratic equation. Now, let's say this is factorable, which I think it is. Yeah, I guess I can show both methods. If we were to factor out a 12, we would get x squared minus, let's see, is that 8? 8 is 80, and 16 is 90. Oh, maybe it's not factorable. Let's just let's just evaluate the quadratic formula. So most of these are going to end up in the quadratic formula anyway. So let's just do it. If we get a whole number, we're in a good spot. If not, we'll figure it out when we get there. So x equals negative b plus or minus square root b squared minus 4ac all over 2a. X equals negative b, so 92 plus or minus, and oops, it will let me do this when I'm screening. Oh, it won't let me do Desmos. Okay, I'm just gonna flip-flop. I'm surprised it won't let me do two screens at once. That's 8464. So even though it's negative, anytime you square negative, it's positive. I just forgot what it was. 8464. Take away 4AC. 4 times 12 times 120. 4 times 12 times 120. 4, 12, 120. 5760. All over 2A. 24. Okay, x equals negative 92 plus or minus square root 8464. Let's see if this ends up being 8464. Take away 5760. Ooh, it's exactly 52. So I bet you this is pretty close to factorable. All over 24. And so x equals, that's 144 over 24, and that's 40 over 24. Absolutely, that was factorable. That's fine. If it was over 12, it would be 12. It's over double that, so I'm getting 6. I'm going to get divided by 8, 16, 24. Divided by 8 is 5, so I get 5/3. So I get 6 and 5/3. Now again, could have factored that. Let's see. Ooh, 6 doesn't work. 5/3 works. 5/3 works. This one does not work. We're going to say outside our constraint or domain. So 5/3 is going to be exactly what we have. Now, if we want volume, we're going to have to say volume is length times width times height. Volume is 5/3 is one of the items. It doesn't matter the order. We're going to do 8 take away 10/3 and 15 take away 10/3. Now, just for the heck of it, I'm going to put this all in terms of thirds. So when we're doing this, 24 thirds minus 10/3 is 14/3. 15, 30, 45 thirds is 35 thirds. Okay? 5, 14, and 35. 5, 14, and 35. 2450, 2450 27s, or, which in a real world example, the approximate is probably a better result here, 90.74, 90.74, whoops, 90.74 inches cubed. Okay, so the value that maximizes is 5/3 inches. These are inches. And our final volume is 90.74 inches cubed. Alrighty, sorry about that. So there is one last thing that I really should do. That is, I should really focus in to see if this is a maximum or minimum. Clearly, my two answers, only one of them works, but there's two ways to do this. It's the first derivative test or the second derivative test. I think the second derivative is going to be pretty nice. I'm going to find second derivative here. Maybe I'll change the color. So the second derivative of volume is, let's see, 24x minus 92. And so when does 24x minus 92 equal 0? So let's see. That's going to be when 24x equals 92. 92 divided by 24 is 3.83. Let's see, what is it as a fraction? It's 23 over 6. Okay, so x equals 23 over 6. It's almost 4. So that's where our concavity is. What we're going to have to do is we're going to have to test the 5/3 value to see if the 5/3 value, this is not good work. I'm all over the place here. But the 5/3 value, we're going to test in that derivative. So let's see. So we have the second derivative at 23 over 6. That's almost the number 4. 5/3 falls right over here to the left of it. If we evaluate 5/3 into that, we are going to get a negative value. Seeing as that was 0, anything less than that you put into 24. 24 times 5 is about 125 divided by 3. Definitely is going to be negative when compared to 92. After that, anything greater than 4, let's say 5. 5 times 24 is 120. We're pulling a positive value there. So here your 5/3, has negative concavity, making it a maximum there. Again, we could have done the first derivative test. I just think that the first derivative test is a little bit more difficult because you're dealing with greater numbers. But again, you take these two numbers, those are your point of focus. You would test in the first derivative. You would test maybe the number 0. That's going to give you a positive 120. Test the number like, I don't know, let's see, that's 1. Maybe test the number 2. 2 is probably going to would have to give you a negative, and then something greater than 6, maybe the number 10 is going to give you that positive that you would need to determine increase, then decrease, then increase. All right. We have one last example here. You've been asked to design a can to hold 2 liters of soup shaped like a right circular cylinder. What dimensions will use the least material? So there you go, least material. So what we're talking about surface area. So for this, we're talking about surface area. And then we want 2 liters of soup. So our volume is 2 liters. To me, that's 2,000 cubic centimeters. Don't forget, 1 liter is 10 centimeters times 10 centimeters times 10 centimeters. Ah, that system of measurement. Very, very nice compared to our gallons. So 1 liter is 1,000 cubic centimeters. 2 liters is 2,000 cubic centimeters. You just double that. There, the metric system, man, that's a great, great system. So we have 2,000 centimeters, and so we've been asked to design this can. So let me sketch out a can here. Boom, we got that. We're gonna duplicate that. Gonna drag this down. It's not perfect, not drawn to scale. Oops, not drawn to scale, but it's good enough here. We have a particular can with radius and height. What I do know about volume of a can is that it's going to be pi r squared, that's your base, times your height, which is height. And what I do know is that volume automatically is going to be 2,000, so we're in a pretty good spot. Pi r squared times height. We know nothing else about it. So let me pause here at the 2,000 equals pi r squared height. We're either going to have to solve for radius or for height. Let's talk about surface area. Surface area is a circle, pi r squared, that's the bottom. Another circle, pi r squared, that's going to be the top. Well, there's no direction in space, but you get what I'm saying, the two circles. And then we're going to have to add to it whatever around it is. Well, around it, if I unravel it, we notice if we unravel this, we still have a height, and we have around this edge. Well, what is this edge here if I unravel it? Well, that is circumference. This is circumference. Circumference, it doesn't look that great, but circumference is 2 pi r. So the area of this particular space is 2 pi r times h. So we have 2 pi r h. We can clean up surface area to be 2 pi r squared plus 2 pi r h. Obviously, we can factor this a little bit if we wanted to. What I'm looking at is my volume is my constraint or my restriction, and I could substitute in for r's, but I think that that could give me a square root, and I'd want to stay away from square roots if possible. It's up to you which variable you want to pick to substitute in for. My thought is there's only one h in this surface area that again, this is my optimization function. So let me just, we said we were trying to look for the minimum amount of surface area. So this is my optimization. Oh, I spelled that totally wrong. Ization. Sorry. So my optimization function is this surface area item. Again, can we do implicit differentiation? Sure. I would really recommend we stay away from it if possible by substituting variables. So I think I'm going to solve this for h only because it really narrows down the amount of work I have to do. Think smarter, try not to work harder if possible. We take this and we substitute it in here. So my new optimization function, 2 pi r squared plus 2 pi r 2,000 over pi r squared. I can clean this up a little bit. I might as well, because as long as r is not 0, which is a good thing, I can assume that my denominator will, I'm gonna go here, I'm gonna get rid of these and one of those, and so I'll just call it 4,000 over r. Or, I'm about to derive this, so I'm going to call it r to the negative 1. Just do it all in one step here, make it nice and clean. The derivative of surface area, so surface area, I'll switch colors. The derivative of surface area is 4 pi r squared. Oh, sorry, 4 pi r. We are deriving it with respect to r, so there is no need for dr dt. We're not dealing with time. We are not dealing with another variable in question. This is derived with respect to r, which is another reason for substituting in for that variable. And we're not looking, this is not a moment, this is all moments in time, not a changing moment in time. So we get 4 pi r minus 4,000 r to the negative 2. So we are substituting this in for 0. So we are looking for where it's a maximum. So it's going to be 4,000 over r squared. I do think the easiest way here would be to move the 4,000 over. So 4,000 over r equals 4 pi r. Oh, sorry, or r squared. Cross products or multiply both sides by r squared. Either way, cross products. If I do this, this is a 1, 4 pi r over 1. We can assume, so 4 pi r cubed equals 4,000. Divide both sides by 4 pi. R cubed is equal to, let's see, is going to be equal to, 1,000 over pi. Did I do that right? Yep. And then we're going to find the cubic root. So r is equal to the cubic root of 10,000 is going to be 10, but this pi here is a cubic root of pi. All right, so we have a location that we're thinking is going to work. It's going to be r equals 10 over the cubic root of pi. So we also need to know what my height is going to be. So we need to find the surface area function. Excuse me. We're going to have to find that where am I right here? Oh, no, we can, you know what? We can take this function and find our height. So 2,000 over pi r squared is going to be 10 over the cubic root of pi squared. So 2,000 over 100. This is pi all over 3 radical pi squared, which can end up in the denominator here. Well, let's see, hold on. We have 2,000. Let me clean this up. 2,000 was in my initial numerator, and so now we have a numerator 2,000 over 1 times the cubic root of pi squared all over 100 pi. That's going to be 20, and it's going to be pi to the 2/3 all over pi. When we start to clean this up, we get, whoops, wrong key. 2,000 divided by 100 is 20. Pi stays in the denominator, and this is 2/3 pi. We can also just call it 20 over pi to the 1/3. So that's equal to height, 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 height. Height equals pi. Yep. Awesome. So those are my dimensions. It doesn't ask how much material is used. It just asks for the dimensions. In this case, we're dealing with centimeters. That's in terms of centimeters. And then R is also in terms of centimeters. Notice that R is, we could say that it's 10 over pi to the 1/3, and H is 20 over pi to the 1/3. Interesting that the radius is half of the height. And it doesn't matter whether you leave it 1/3 or pi over the cubic root of pi, it all works out. Okay. That's it. We're going to go on to some flipped math in a second. If you'd like to stay tuned, if you think you got the flipped math, you can do it on your own. Okay, so we're back with some flipped math, and I really like some of the problems that are asked in here. They're repetitive, so I won't redo those problems. For instance, like number 1 is repetitive, and so is number 3, involving the open top box and then numbers multiplied together. All that information is still here. The strategies for solving. In flipped math, it's 6-3 for the longer class, and then I think it's 5-10, 5-11 for the shorter classes. So some of this is repetitive. Notice 5-10, it still has a sum of 30 and still got the same kind of problems. So let's do 2 more problems in the 6-3 example. The first one we notice for what point on the graph y equals the square root of x is closest to 5-0. There's a few ways to think about this. When I look at it, I'm like, okay, how do I get, like, is this closest to 5-0? Probably not. Is this close to 5-0? Probably not. What about this right here? What about this right here? What about this right here? I think we're getting closer. What we notice is that one's definitely not an option. If we were to look at distance formula, it would probably help to tell us what's going on with this. So I'm going to pick a random point on here. I'm going to call it x comma the square root of x. The reason why is that if I put in an input here, my output is equivalent to the square root of x. So I do know that that is a location, and if I want another location using the Pythagorean theorem or the distance formula, this is my other one, 5-0. That one's straightforward, it's numeric, and it's pretty easy to work with. One of these that I drew is probably close to where I want to go. What I It's probably one of these that I drew is probably closest to the 5-0 point that we're looking for. Again, we can use any function we want. The square root of x is the current one that's given. So I'm going to write the distance formula. Distance equals the square root of delta x squared plus delta y squared. It's the difference of my x's times the difference of my y's. So what I'll do, and it doesn't matter, these orders don't matter, as long as when you substitute in your numerical and variable inputs and outputs, you do them consistently in the same order. So what I'm going to do is I'm going to rewrite it as x1 minus x2 squared plus y1 minus y2 squared. And let's make that look like a 2. Okay, so I'm going to try to put it in a really nice form here. I'll say that the distance is equal to, I'm going to go x minus 5 for my x's, and then I'll do for my y's the square root of x minus 0. So x minus 5 squared, and then it will be the square root of x minus 0. I'm going to derive this later on, squared. Let's clean it up a little bit. So x squared minus 5x plus 25 plus the square root of x squared is x, the absolute value of x. So my new distance is x squared minus 5 plus 1 is minus 9x plus 25. Okay, I'm ready to find the derivative now. So the derivative of distance is equal to, this is all to the 1/2 power. So I will, instead of rewriting it, I'm just going to call it this to the 1/2 power. Drop the 1/2 down, take 1 away, you get negative 1/2. Do not forget the famous chain rule, 2x minus 9. You have to derive that inside. So right now you had the square root of that. So that's x to the 1/2 power. So it's something to the 1/2 power. You drop the 1/2 down, you take 1/2, you take 1 away, and you get negative 1/2. You do have to derive the inside to make sure we make up for that difference. So we now have the derivative of distance is equal to, I'm going to clean it up, 2x minus 9, multiply the 1/2 times the 2x minus 9. So it's just 2x minus 9 all over 2. Then this thing here can move to the denominator because it's the 1/2. I can call that the square root, or I can just leave it as 1/2. It doesn't matter at the moment because I'm going to substitute in 0 for distance, for the derivative of distance, which, as we know, we're only interested when the numerator is equal to 0 for a possible critical point, and I'm also interested when this doesn't work out, but I think we're good to go with just the numerator. So 0 equals 2x minus 9, 2x equals 9, x equals 4.5. Ooh, that number looks really, really good. Wow, I didn't even realize that was going to work out like that. So it does look like 4.5 will be the shortest distance between 5, 0 and the function. We do need to work with either maybe the second derivative, or you know what, I'm very much not interested in the second derivative for this function. That would involve, think about it, the quotient rule, another chain rule. Yeah, I think I'm just going to do the first derivative test here at 4.5. Okay, so so we're going to do the first derivative test to make sure that this is a maximum, or sorry, I apologize, a minimum. Now, what's interesting is we're not actually looking for when this function has a max or min. We're not looking for when its slope is positive or negative. We are looking for what we derived, which is the distance formula. So we're interested in when the distance itself is positive or negative in terms of its increase or decrease, and if it has a max or min. So we'll take that 4.5, we'll evaluate it in. This should work out for us. I'm going to pick the number 1. I'm going to pick the number 5. So if we go to evaluate 1, we have 1 minus 9 is negative 8 plus 25. That's positive. The square root of a positive number is positive times another positive is positive. In the numerator, you get 2 minus 9 is negative 7, so we get a negative over a positive, which is negative. So in this case, we get the negative right here. For 5, we're going to get 25 and another 25. That's 50. Take away 45 is 5. That's the square root of a positive is positive times another positive is positive. And then in the numerator, we get 10 minus 9 is 1, which is positive. So positive and positive, that gives us a positive. Don't confuse your first derivative test here. That's what I did accidentally in the last video. I had to cut that part out. We're not looking for where this is increasing and decreasing. We are looking for where this distance, which is every one of these, is shortening, as we see there, and then getting longer. So if it's shortening, getting longer, we get to shortening and then longer, we get to a minimum. There we go. So 4.5 is our minimum value. So at what point on the graph? So the location on the graph, closest, what am I doing? Closest to 5, 0 is 4.5 comma the square root of, let's just say 9/2 comma the square root of 9/2. Ooh, you know what we can do? We can call it 3 over the square root of 2. If we find the square root of 9/2, that's equivalent to the square root of 9 over the square root of 2. So 3 over the square root of 2. I'm just doing math in my head there to get it a little more reduced. Sweet. Okay, our next example, this one's a famous one as well. We're going to skip the cards in the open top box because we did one like that. We're going to go over the two towers are 30 feet apart. Okay, so we have two towers. One is 12. Let's see, one is 12 feet high. The other is 28 feet high. Oops, that didn't work out well. Cool. I'll just close them off then, if that's what works. 28 feet not drawn to scale. There is a stake in the ground between the towers, so we're going to put a stake somewhere. It could be anywhere along this. But just for the context, I know it's going to be closer to this one. Only because I've done so many of these problems before where I know that the shorter distance is compared to the shorter side as the longer distance is the longer side. You'll see that when we end up solving this. So I'll draw this diagram to scale only because I've seen it before. There's a stake in the ground. The top of each tower has a wire tied to it that connects the stakes. Where should the stake be placed to use the least amount of wire? All right, so I'm going to call the entire wire 1 plus wire 2. I'll call this wire 1 and this wire 2. We clearly see that there's some form of a Pythagorean theorem that might be working here. I'm going to draw this in from base to base. I'll call this x and I'll call this 30 minus x. It doesn't matter which one you call x. Whatever answer you get, you'll just adjust. If I put, oh, that's not going to work the way I want it to. I'll just leave it. If you put 30 minus x for this one, then when you solve for this one, it will all work out. It doesn't really matter which one you set equal, which x you have and which one you have is 30 minus x. So our distance formula is going to be, for the first one, the distance is going to be the square root of x squared plus 12 squared. So I'll say that wire 1 equals the square root of x squared plus 144. That's to find this y1. So I just did leg squared plus leg squared equals hypotenuse squared. For this next distance, it's going to be the 30 minus x squared plus 28 squared. I'll call that W2. Call that 900 minus 60x plus x squared plus 28 squared. 784. You're definitely going to need a calculator for this one. What did I do? 784. The numbers are just too large to do this one strategically without a calculator. We're going to get x squared minus 60x. And that's 1684. Okay, what I know is that I want to minimize the amount of wire. So wire is equivalent to, I'll just pull it down here. Wire is equivalent to wire 1 plus wire 2. So total wire is equal to the square root of x squared plus 144 plus the square root of x squared minus 60x plus 1684. Now, if I want to minimize total wire, we have to do w. So if I find the derivative of w, I have to find the derivative of w1 and w2. So I'll just come out and say that the w is so w prime is equal to the derivative of this one, which is 1/2 x squared plus 144 to the negative 1/2. Don't forget, we have to times by 2x, which is the derivative chain rule part. The second one is 1/2 of this to the negative 1/2, and another chain rule, so 2x minus 30. Oh, shoot, I messed that up. 2x minus 60. All right, I'm already thinking about that 2 there. I can clean this up a little bit. The y prime is w prime is equal to x over, I'm going to get rid of these. See these 2's? So x over x squared plus 144, the square root of that. Same thing here. The 2 will be a 1. I'll get a 30. Get rid of that 2. So I get x minus 30. So I'll leave this as x minus 30 all over the square root of x squared minus 60x plus 1684. Woo-wee, that's crazy. You know, I'll change the color because I'm switching ideas. Okay, now I'm going to set that equal to 0. Now clearly this is not a nice one to solve for. You're going to use your graphing utility, throw it in the graphing utility, and find out where it crosses the x-axis. I don't have the ability to do that on this iPad, so what I'll do is I'll use Desmos. But what you would need to do is in your y equals, you would have to type in this equation, and you'd have to then look for an intersection of the x-axis using, I think it's second for whatever that whatever the code is at the top there, but I forget. I don't have my calculator near me. So x over the x squared plus 144. I'm going to add to, I think it's addition, another fraction, x minus 30, I believe. Let me go back. X minus 30, x squared, 60x, x squared minus 60x, 1684 plus 1684. Okay, so we have a graph like this. We're looking for the intersection. So in your TI-84, you would calculate it. Oh, it's exactly 9. So we're going to say x has to equal 9. So if x was equal to 9, if here x was equal to 9, then 30 minus x is equal to 21. So here this is 21 feet. This is 9 feet. I'm going to move everything down slightly so it works out well. Nine feet, 21 feet. What's really cool, you notice where this works out, so that 9 is to 12. So 3, 6, 9, 12, 7, 14, 21, 28. It evenly created, what we pretty much did was the minimum distance of this entire wire is when we have a perfect scenario of similar triangles. And anything off of that, we're not going to get a minimum, but it's kind of beautiful math here where 9 is to 12 as 21 is to 28. You can't just set up your proportion and make it work. You have to use calculus techniques to figure it out, but we notice that that is something that happens. So it says, where should the stake be placed to use the least amount of wire? We're going to say the stake is placed 9 feet away. S-T-A-K-E, yep. The stake must be placed 9 feet away from the shortest tower to minimize the wire. Again, I would use, first derivative test. I'm not about to find the second derivative of this one. Anything prior to 9, you can use. So when I do my first derivative test here, let's see, the first derivative, where clearly the wire has to be at least 0. We're going to look at 9. When you go to put in your first derivative, let's see, let's pick the number 0 or 1. Let's do 0. We're going to get 0 here for this one, and then you get a negative 30. So it's the negative, and then 0 here. That's 0. You get square root of 1684. That's positive. So we get a negative over a positive with 0 on this side. So we get a negative result. Even at 1, it will be negative. Let's just check it out. We get that's all positive. You get negative 29. Again, this isn't going to, 1684 is going to definitely override that. So you'll get a positive. So that's done. When we put in let's see, when I put in 10, that should change the game here. 10, it would be 100. Let's see, is it minus? So we're looking for a plus in this space. Let's see. So first derivative, let's pick the number 10. So we get a positive and a positive. Here we get a negative and we also get a positive here. So this one's negative, that one's positive. But we have to see what kind of positive I have. This one's going to end up being greater. You're going to have to do this one in your calculator um, to see what 10 ends up being. I have the ability of just, grabbing a table here. We notice that, what is it, 9? So let's do 7, 8, 9, 10. 10 ends up yielding finally a positive for us. It's very slightly positive. Again, you would use your calculator to figure that out. 10, 11, 12, they all yield positives. So we would know that we have a negative and a positive, meaning that 9 is a minimum. All right. I mean, I think we've hit a lot of them. We have everything's a little different. Like, what is the smallest product of two numbers, given that one number is exactly 7 greater than the other? You would set up something similar where one number is exactly 7 greater than the other. Um, this one, boom, boom, boom. They're all a little bit different. So I'm going to let you practice those. Our goal is to practice those in class after you watch this video. I don't, I could do these all day, but I think if you all practice, then you'll figure out what you need to do after you draw a picture, create that model that needs to be optimized. Make sure you label a restriction or constraint. Try to get everything down to that single variable. Figure out if it's a min or max, especially using calculus. We have to use the calculus, derivatives and second derivatives, and then make sure we test our endpoint after after we can, if we're looking for mins and maxes, all right, which we are. All right, have a good night.